Hello, my name is Anders Pettersson, and today I'm going to talk about engines, about internal combustion engines. First, some outline of what I'm going to talk about today. We have some definitions. We'll talk about the fuel to air ratio. We'll talk a little bit about forced induction and volumetric efficiency. We touch on engine efficiency, and we will round up with exhaust after treatment technologies. What is an internal combustion engine? Yeah, the combustion inside the engine. So you have internal combustion, you get an expansion of the gases, you get a linear movement that is converted to rotational movement. And that could be compared, for example, on external combustion engines. You see here the Stirling engine. You have the fire outside the engine. Here in the internal combustion engine, you have the combustion inside the engine. Let's talk about some definitions. Here we have a piston and a cylinder, and both of them have the diameter d. Distance that the piston travels from bottom to the top is the stroke. And here you could see, here we have the top dead center where the piston is the uppermost position. And here the piston is in the bottom dead center where the piston is in the lowest position. This green area is the displacement, the volume of the cylinder. And there is also another volume. We have the clearance volume. That is the volume of the combustion chamber, the volume that is remaining where the piston is in the top dead center. And by the clearance volume and the displacement, the compression ratio could be calculated. And the compression ratio is the relation between the displacement and the clearance volume. That is a very, very important design parameter on an engine. We also have the compression pressure. It's something different from the compression ratio. The compression pressure is measured by installing a pressure gauge inside through the cylinder, through the spark plug or another connection like an injection nozzle or something, and then the engine is cranked and the pressure is measured. And that's typically used to diagnose if the engine is in good condition. Here you could see you have measurements for a 4-cylinder engine, and you see here this one has that compression pressure, and here you see cylinder 3 has a very different compression pressure, and that indicates that something is wrong in the engine. And it's very important to keep in mind that the compression pressure and the compression ratio is not exactly related to each other. Another important thing regarding engines and combustion is the fuel to air ratio. In theory, the optimal point to stoichiometric mixture is 14.7 parts of air to 1 part of fuel by weight. But you should remember that air is very light. It's only 1.3 kilograms per cubic meter, so it corresponds to about 10,000 liters of air to 1 liter of fuel. When talking about mixtures, you either talk about the ratio or the lambda value. You see the lambda value here, the Greek letter, and lambda value 1 corresponds to a stoichiometric mixture of 14.7. If the lambda value go down, you go on the rich side with more fuel compared to the air. And if the lambda value goes up, it goes to the lean side where you have more air compared to the fuel. Let's talk about volumetric efficiency and forced induction. The volumetric efficiency is how much is inside the cylinder compared to the theoretical value. For example, if you have an engine, one stroke make it to suck in 1 liter of air, but inside the cylinder it's only half liter of air, then the volumetric efficiency is 50%. Like here, you have an engine, here you have a throttling device that is partly restricting the airflow into the engine, and that makes the engine only fill up to 50%. In this case, you have an ideal engine, the throttling device is open, and the engine is filled up to 100%. It is possible to increase the volumetric efficiency to slightly over 100% by tuning the intake and the exhaust system. But if you want to go really much further, you need to introduce the forced induction either by turbocharger or supercharger. Then you put some kind of device that take in air and force it into the engine, and then you could reach over 100% in volumetric efficiency. A common way to increase engine performance is turbocharging. And the turbocharger is an exhaust-driven supercharger. Here you can see a picture of it. It consists of two parts. You have the turbine part, and you have a compressor part. Here you see a cutoff of it. Here you see the turbine is driven by the exhaust stream, make this shaft to rotate. Here in the middle you have the bearings. It's either Jornard bearings or bore bearings. The rotational speed is very high. It could be over 100,000 RPMs. And here the compressor is sucking in air and it pushes it into the engine to increase the performance. One of the drawbacks is that the turbo could take some time to spin up. That is called the turbo lag. Another type of forced induction is the supercharger. And the supercharger is a mechanical driven supercharger or compressor. There are many different models and there are no delay for the boost. It could either be of screw type, you could have the Roots type supercharger, or the centrifugal supercharger is more like a mechanically driven turbocharger. One of the drawbacks with a supercharger is that it takes some energy from the engine's crankshaft to rotate them. When compressing the inlet air is not only increase in pressure, it also increase in temperature. And to prevent the engine from knocking or other intake components to get damaged, there could be need for charged air cooling. And the charged air cooler, it increased the volumetric efficiency, it lowered the emissions, and it increased the engine power by cooling the intake air. To using a strict terminology, it should be called an aftercooler, but everybody in the industry say an intercooler. And it could either be of air-to-air type. Here the intake air goes inside and ambient air is cooling the charged air. In this case, you have the intake air going through this, and then you have water that flowing and cool the intake air. Let's talk a little bit about power and torque. Here you see a chart for a 4-stroke Otto engine and a diesel engine. The red one is the power, the green one is the torque, and here you have the engine speed and the engine power in kilowatt. It is possible to calculate the power by taking the torque and multiply it with the angular velocity omega. Here we could have an example. In this engine, you have a maximum power of 105 kilowatts at a speed of 4,500 RPM. To calculate the torque at the maximum power could be done by this. We just take the power here in watts, divided with the speed, and we calculate the angular velocity by P divided with 30. And then the answer will be 220 Newton meters. And here you could see in the chart, just under the peak power, the curve is at 220 Newton meters. Let's talk about engine efficiency. You could either express the engine efficiency in percent or something called BSFC, the brake specific fuel consumption. In the United States and for recreational vehicles, it's very often used the quite strange unit pound per horsepower hour. But the SI unit is gram per kilowatt hour. Another thing about engine efficiency is the brake mean efficient pressure. That is the mean pressure over the complete cycle of an engine. And that value could be used to compare the performance of completely different engine designs and engine sizes. Here we have an engine efficiency map for a big diesel engine. Here we have the torque, here we have the speed, and on these lines, on this what we call a muscle chart, you have the BSFC in gram per kilowatt hours. So you can see here, at low load and high RPM, you have a very bad efficiency. On medium RPM and very high load, you have the best efficiency. Here it's down to 185 gram per kilowatt hours. So when designing a vehicle and choosing the engine and choosing the transmission, it's very, very important to make sure that you end up in the high efficiency area as a big part of the driving cycle as possible. So you don't go down around here. This chart is showing a normal passenger car in a city drive cycle, equipped with a 1.9 liter normal engine. On this here you have the engine speed, you have the engine load either by torque or by the BMEP, and here you see the efficiency of the engine, and up here you have the sweet spots where we have the highest efficiency. These black dots corresponds to the driving in this city drive cycle, and as you could see, very few of these spots are inside this sweet spot. Quite a big part of it is either around here, idling or cruising at very low loads and low RPMs. Just a few of them is up there where you have the high efficiency. And this could partly be overcome by either downsizing the engine or hybridization or a combination of thereof. Where does really the engine goes? Here we have a 4-stroke gasoline engine. You have some fuel in the fuel tank. It goes into the engine, it gets combusted, and some of the power is transmitted to the wheel. But about 30% go out to the exhaust as a heat. About 30% go to the coolant as heat, and about 4% is consumed as friction. And that leaves only 36% to the wheels. But we should remember, this is at maximum efficiency. That normally, of course, at maximum torque. And if you remember the previous slide, how often do you really drive the car at maximum torque? Not so often. And then you have the same thing for the diesel engine. You have slightly losses in exhaust and coolant. You have some more friction due to the higher combustion pressures, but you have a much higher overall efficiency. And also one benefit with the diesel engine, on partial load, is have typically much better efficiency compared to a gasoline engine. Okay, that was all for this session, but it will continue in the exhaust after treatment show. Thank you.